Welcome, everyone. Thank you for joining us for the latest episode of our Gleeble webinar series. My name is Dan Quigley with DSI, and I'm happy that you could join us. On behalf of the whole team at DSI, we hope this message finds you and those around you safe and healthy. Today's webinar is titled The Role of Physical Simulations in Welding Electrodes Development, presented by Dr. Murugaiyan, Amirthalingam, or Dr. Muru for short. He is an assistant professor and head of the Joining and Additive Manufacturing Laboratory at the Indian Institute of Technology in Madras. And I also want to take a minute to thank the Indian Gleeble community. Back when the pandemic began and many of us went into lockdown, our partners at DTS and several experienced Gleeble users in India came up with the idea for this webinar series. And we thought we would start out small, and we scheduled a short webinar, and we were pleasantly surprised with the great turnout. Based on that results, we expanded the webinar series from there and invited the rest of the world to join. And today is our 31st weekly webinar with presenters from all around the world. But we are grateful for the passion and expertise of the Gleeble community in India, of which Dr. Muru is a key figure. For this week's presentation, we're going to try something a little bit different. Dr. Muru has pre-recorded his presentation, which I'll play in a moment. However, he's also here in the webinar live and is able to answer questions either during the presentation using the chat tool here in the webinar, or I can answer some questions live following the presentation. But all questions should be submitted through the chat message here. So type your questions in, and they can either be answered during the presentation by Dr. Muru live by him typing in responses, or if we have time, we should have time at the end, we can answer those questions live. Video of this presentation will be available online soon. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and click on the resources link in the top navigation bar. Then click on webinars. There you can view recorded webinars and sign up for future webinars. But as a quick scheduling note, there will not be a webinar next week on November 26th because of the Thanksgiving holiday here in the US. But there will be a webinar the following Thursday on December 3rd. And a registration link and description are available on our website. The December 3rd webinar will focus on assessing creep damage of service-exposed power plant steel through creep deformation measurements using digital image correlation. Thorsten Becker from Stellenbosch University will present joint research from the team at the University of Cape Town in South Africa. And they've shown that a wealth of deformation data can be extracted from very few specimens, which is highly beneficial in characterizing material integrity. But that's enough about me talking. Let's get to our expert presenter. As I mentioned, Dr. Muru has pre-recorded his presentation, but he is here in the webinar live, so if you have questions, again, please do type them in. We have a lot of people on the call, but I hope we'll be able to address most of your questions. In a moment here, I'll start the presentation. I hope you enjoy it.
Good evening to all my friends in India. Good morning to my friends who are attending this talk from USA, and good afternoon to all of other colleagues and friends who are attending from elsewhere. So my name is Murugaiyan Amirthalingam, and thank you for attending this talk through webinar medium. Let's go into the talk, what I'm going to give for next 30-40 minutes. The title of the talk I'm going to talk about today is the role of physical simulations in welding electrode development. So just a brief introduction about myself. My name is Murugaiyan Amirthalingam. So I'm an assistant professor in the Department of Metallurgical Materials Engineering. So I'm also the head in charge of joining an additive manufacturing laboratory in this department in IIT Madras, Chennai in India. Right, so the outline of the talk I'm going to give is presented here. So the first topic I'm going to cover is the complex phase containing the high strength steels. Why are they important, and how we stabilize these complex phases by carefully modifying the alloying elements as well as the heat treatment. And these steels are extremely challenging to weld because of the presence of high amount of alloying elements and the complex base metal microstructures. And recently we developed some strategy to weld these high strength steels by developing unique electrodes, and we used extensively Gleeble to optimize the welding electrode chemistry as well as the welding procedure. So I take this opportunity to present our recent activities on welding electrode development for the high-strength steels. Right, so we use Gleeble extensively to understand the hard cracking susceptibility, and we optimize the electrode chemistries based on the weld thermal cycles we'll have to subject to obtain these complex phase containing microstructures in the weldments. And I'll summarize the results and acknowledge my colleagues who helped me doing this work. So the high-strength steels, what we are actually discussing over here, they contain the ultimate tensile strength beyond 1 gigapascal, right? And they also possess a very good ductility for this strength level, about 10 to 15%, so that these steels can be made into components for applications like armor applications and automotive applications for lightweighting primarily and shipbuilding. So the unique microstructure what the steel possess, okay, so they make these steels very attractive for high strength applications. So for example, shipbuilding and these steels can expose to hydrogen containing environment. So the unique microstructure what we see here in this slide, the mixture of retained austenite and carbide-free bainite containing microstructure are also known to have a very good resistance against hydrogen, and because of the increased interface boundaries as well as the presence of retained austenite, which can also store hydrogen in the microstructure so that the embrittlement can be delayed. So this microstructure becomes very attractive for high strength applications. Moreover, the carbide-free bainite containing microstructure is also known to have very good ballistic resistance. So therefore, for armor applications, this becomes very interesting. Unfortunately, because of the high carbon containing microstructure with the other aligning elements which are needed to stabilize this structure are extremely important, and they also affect the weldability significantly. So in order to develop good welding electrodes, so we need to understand how these alloying elements affect the weldability of the material. So therefore, the physical simulations becomes very critical, right? So these microstructures are stabilized by the addition of complex alloying elements and heat treatment cycle. So this slide I show you how a retained austenite containing microstructure can be stabilized. So where the base materials are taken to temperatures of austenization, either in a fully austenization condition or in intercritical annealing temperatures where both ferrite and austenite can be coexisting. So both the microstructure, either in a fully austenitic condition or in intercritical condition, upon heating to these temperatures, they are cooled to isothermal bainitic holding temperatures, where the austenite is left to transform into bainite. So during this transformation, when the austenite transforms to bainite, okay, so we suppress the cementate precipitation such that the bainitic ferrite, okay, stabilizes with the supersaturated carbon, and the suppression of cementate precipitation ensures that the untransformed retained austenite, the untransformed austenite can get enriched in carbon. So therefore, it can be stabilized to in the microstructure upon cooling from the bainitic holding temperatures. So the addition of alloying elements such as silicon and aluminum is very important because these elements are known to suppress the carbide precipitation during this bainitic holding. Right. Apart from silicon and aluminum, sometimes we also add phosphorus. Okay, because phosphorus can also give very good solid solution strengthening, and it can also suppress cementite formation. So this isothermal holding the cycle is extremely important to get the carbide-free bainite containing microstructure. And so we also need to add alloying elements, silicon, aluminum, phosphorus with the carbon, so that we can stabilize retained austenite is about 10 to 15%. So this thermal cycle with an alloying element additions is extremely essential to stabilize these microstructures, right? So, but if you understand the welding metallurgy, so these elements are very notorious for welding, right? The moment you increase these alloying elements concentrations, we embrittle the microstructure, okay, and we can also make the microstructure susceptible for hot cracking, cold cracking, and also we can stabilize unsolicited phases in the microstructure. So again, the partitioning of carbon is doing the trick to stabilize this CFB microstructure, the carbide-free bainitic microstructure. So when we do an isothermal holding, so we form the bainite with enriched in carbon, supersaturated carbon, so that the bainitic ferrite strength can be increased. Subsequently, the suppression of cementite ensures that carbon is partitioned into the austenite, so that austenite can be stabilized when cooling from these bainitic holding temperatures. Okay, I don't want to go into detail about the partitioning because of time constraint here. So you can also refer some of the references what I quote over here. Right, so the trick over here is the microstructure is stabilized by using this isothermal bainitic holding. But so if you look at a typical weld thermal cycle, we cannot do such a heat treatment, isn't it? Right, because when you look at the weld is actually cooled directly from solidification temperature to room temperature. So how do we stabilize this the microstructure? What I showed you in earlier slides. So we'll have to play around with the cooling cycles and understand the phase transformation behavior when the weld pool is solidifying from the solidification temperature to room temperature, and can we manipulate these weld thermal cycles such that the microstructure welds can contain the carbide-free bainite and retain austenite containing microstructure. So that's what I'm going to present in this talk. So the primary welding process we use to weld such steels are the flux-based electrode containing processes, primarily shielded metal arc welding or flux core arc welding. So I'm going to present this lecture henceforth with respect to the development of electrodes for shielded metal arc welding processes. And this process is also known as stick welding process because the electrodes are actually made into a stick, right? So this electrode primarily contain a metal core and the fluxes added onto the surface of the electrode. So the alloying elements that are required to be present in the weld pool are either added into the metal core or in fluxes in terms of ferroalloys, and these fluxes ferroalloys decompose and produce molten droplet from the melting of the electrode, and subsequently the molten droplets get transformed to the pool, and the weld pool solidifies, and subsequently based on the thermal cycle that is imposed when the weld pool solidifies, we may stabilize the microstructure. So the ISP video just shows how the actual process works, and we have an arc ignited between the electrode and the weld pool, and from the heat generated in the arc, okay, the flux decomposes, the ferroalloys get disintegrated to generate the alloying elements that are required in the melt, and subsequently metal core also melts and droplet is transferred from the electrode tip to the base material. So the electrode generally contains a rutile-based flux because of smooth burning and no spatter and fume generation, and rutile-based electrodes are also known to generate hydrogen. And the hydrogen induced cold cracking can be a big problem. But so this is one of the electrodes which can ensure that the self-lifting of the slag, so the slag intrusion can be avoided. So therefore, we still prefer to use a rutile-based electrode despite the problem with the hydrogen induced cold cracking. But we can play around by carefully controlling the weld thermal cycle, which is what I'm going to discuss in next few slides. So the weld compositions is achieved by carefully designing the flux formulation, the electrode core, and the dilution from the base material, right? So now we'll straight away dive into how we can generate an electrode to weld the carbide-free bainite containing the high-strength steels. So to begin with, we start understanding the effect of alloying elements on the solid-state transformations. Right, so we use a combined the mathematical calculations and the physical simulation approach. So we identify some base chemistries and which can give us an bainitic transformation at short time durations when we hold it at isothermal holding. So for example, I show one such candidate chemistry, and we calculate the CCT diagrams using a commercially available neural network database and the thermal database, for example, ThermoCalc, and we construct the CCT diagrams for this chemistry. Right, so these identify chemistry. The important factors are, so the martensitic start temperature should be as low as possible, and the bainitic transformation should be as fast as possible. So therefore, by holding a shorter time duration, we can achieve the isothermal bainitic transformation, what I described in earlier slides. Like for example, the candidate chemistry, what you see over here. So even if you are cooling at a very slow cooling rate, and so we may only transform to primarily the bainitic microstructure. Right? If you are, for example, holding at 400 degrees centigrade, so the transformation can be completed in about 100 minutes or so based on the CCT prediction. And apart from the CCT diagrams, we also predict what is known as an allotropic phase boundaries, and that is to ensure the maximum carbon partitioning when the austenite is held in isothermal bainitic holding temperatures. So we identify the candidate chemistry. So once we identify the candidate chemistry, so what we do is we design the electrodes based on these candidate chemistries with the variation in the alloying elements, which can give us some freedom to play around with respect to the weldability. Right. So first we identify the candidate chemistry, and then we make the electrodes with a plus or minus of 0.3% of carbon, and the other alloying elements suitably buried. So once we make these electrodes and we start producing the candidate welds to generate samples for the physical simulations, because so immediately when we start depositing the welds, the welding thermal cycles are not optimized, right? So we generate the candidate the welds, and subsequently we extract the samples from the candidate welds and carry out extensive physical simulation using Gleeble. Right. So first simulation what we carry out from the candidate chemistries is to understand the hot cracking susceptibility. Because if you look at the chemistries what I showed you in earlier slides, so this is containing carbon is about 0.35 to 0.5. So if it is 0.4% carbon, the material is already highly susceptible for hot cracking. And apart from the carbon, we also have high manganese and chromium, for example, and some amount of phosphorus and sulfur as well from the fluxes what we add. And that chemistries are notorious for hot cracking. So if you don't control the alloying elements in the weld, we end up just producing a cracked weld. So one such weld is actually shown on this video, where we are actually doing a bead on plate on a retained casting containing steel. So instead of actually welding, we are actually cutting. So this cutting, what you see over here, is nothing but a hot crack, which is actually forming and progressing continuously. Instead of welding, we are actually breaking the weld as a cut, right? So, and this is a not optimized condition, right? So from the identified candidate chemistry, if we straight away start doing welding, so we have a problem, isn't it? So therefore, we have to identify with the identified chemistries, so what compositions can give us the welds without any hot cracks, right? So how do we understand the hot cracking susceptibility? So we can either look at the in situ microstructure during solidification, right? So we can also look at in the laser confocal microscopy, where we can also actually visualize the solidification of the weld pool using a laser confocal microscopy. So this is a very expensive affair, right? So where we can see the actual solidification of weld pool and see whether the backfilling is happening during solidification, where the liquid can backfill and arrest the crack. Right, and subsequently, when we do an in situ studies, we can also see the crack formation in situ live by these high temperature microscopy. Right, as I said, this is very expensive affair, so we need to have proper equipment, right? And it is also very challenging to visualize the microstructure during solidification with very high temperatures for this weld. So best is to have the susceptibility measured using Gleeble, isn't it? So to understand the hot cracking susceptibility for the candidate chemistries, so we carry out hot ductility test. Right, so this is one of the best methods to understand hot cracking susceptibility. Right, so we take the samples from the candidate chemistries and we identify hot ductility as a function of temperatures. Right, three important temperatures we'll have to identify. So the first is the nil ductility temperature, the temperature at which the material loses its ductility completely. So, and then subsequently, by increasing temperature stepwise, we can also identify the temperature at which materials loses its strength as well. So the difference between NDT and NST can give us indication about whether liquefaction phenomena is predominant. So when the material is heated up to the various temperatures during welding. And subsequently, when we start cooling the weld and do the testing as a function of cooling temperatures, we can identify the ductility recovery temperatures and DRT temperatures. Again, they are indicative of the solidification range from which the weld is actually cooling and then subsequently solidifying completely into a solid structure. So if the difference between the NST and DRT is actually larger, then we can say that the material is solidifying in a larger range. So the solidification cracking susceptibility temperature range would be larger. So therefore, material can be susceptible for hot cracking, okay, during cooling. So the difference between these temperatures give us a good indication about the hot cracking susceptibility of the material. So once we identify the candidate chemistries, so we carry out extensive hot cracking test by using Gleeble hot ductility testing, right? So then we can optimize the chemistries based on these hot cracking susceptibility test. So I'm showing such an optimization. So the left side figure shows the detailed signatures of an austenite filler A286 I borrowed from Professor John Leopold's book, right? So this is one of the fillers commonly used to weld the carbide-free bainite. So and if you look at the actual the hot cracking susceptibility from this Gleeble ductility testing, the difference between the NDT, NST, and DRT is huge. So therefore, this material can be highly susceptible for hot cracking. But with the optimization of the chemistries, so the candidate chemistries can be tuned such that the temperature range between the NDT, NST, DRT can be reduced significantly. So this is carried out in all weld carbide-free bainite welds from one of our colleagues, and it clearly shows that by carefully modifying the chemistries, we can reduce the hot cracking susceptibility very well. So Gleeble helps us to understand the hot cracking susceptibility, and carefully tuning the chemistries, we can also identify which chemistry has the least susceptibility for hot cracking. So once we get away with the hot cracking susceptibility problem, right? So next is to identify the actual weld thermal cycle. So the weld thermal cycle means here is to identify both the interpass temperatures, the temperature at which the second pass is deposited on the first pass. So the interpass temperature is one of the important parameters because that led the first pass weld to transform into isothermal bainitic temperatures. So upon maintaining the interpass temperatures, once the welding is carried out, we also have to maintain the entire weld into an isothermal holding temperature so that the weld can be transforming into an completely carbide-free bainite containing a microstructure. So how do we identify these temperatures? Right, I showed you in the earlier graphs. So the CFB microstructure is stabilized by using an isothermal holding, right? So once we optimize the chemistries, so we take the samples from all welds and then we carry out extensive diatometry analysis. So the purpose of diatometry analysis is to identify the interpass temperatures and post-weld isothermal holding and time and temperature, right? So what we do it again. So from the hot cracking susceptibility, so we can identify the possible chemistries subsequent to the hot cracking test. So I'm showing you three chemistries which is optimized in this case, right, based on the CCT and subsequently hot cracking test. We identify these three the chemistries, and then we actually make the weld deposits using these chemistries. So when we make these three chemistries and welds, and we take the samples for Gleeble simulations to understand the phase transformations, right? So we take the samples from these multipass welds, right, and then subject these samples for various electrometry analysis. So I'm just going to show you a case study for these chemistries. How do we optimize the interpass temperatures and subsequent isothermal bainitic holding time and temperatures when we do post-weld heat treatment. So based on the chemistries, we can carry out the electrometry analysis to understand what temperature we'll have to hold it between the process and during post-weld heat treatment. Right, so three chemistries I show you: alloy A, alloy B, alloy C. Okay, so I mean, you don't need to worry about the actual chemistries. We just assume that we are going to see three steels: alloy A, alloy B, and alloy C. Right, alloy A. So we can identify the suitable by some bainitic holding temperatures, and as well as we can vary the temperatures and identify what is the transformation kinetics using the automotive analysis. Right, the important condition to generate carbide-free bainitic containing microstructure is the final microstructure should not contain any martensite. If a martensite is present, so obviously the structure becomes brittle, and the structure becomes susceptible for hydrogen-induced cold cracking. And we should also understand these temperatures of holding should always be above MS temperature. So therefore, we carry out the extensive electrometry analysis by understanding first the martensite start temperatures, MS temperatures, and what would be the ideal the isothermal bainitic holding temperatures. Right. So we carry out extensive experiments at various temperatures. I'm just showing you the two such isothermal bainitic holding conditions, just to give an idea about how the changes in these isothermal bainitic holding temperatures can change the microstructure, and subsequently how we can optimize it. Right. So we can now understand the exercise of optimizing the interpass temperatures and the post-weld isothermal bainitic holding temperatures, right, by looking at these three conditions. So just to make the presentation clear, now we can assume three conditions: the alloy A, the complete martensite transformation, and the bainitic holding 1, bainitic holding 2, similarly for alloy B and alloy C. So if you look at the alloy A, so we need to identify first martensite start temperatures, MS temperature, right? So we can identify, and we'll have to ensure that the isothermal bainitic holding is always above MS temperature, right? So the important condition, as I told you, so whatever temperature we are holding and subsequent cooling to room temperatures, it should not transform to martensite. Unfortunately, if you look at an alloy A, right, the thermal cycle, what we used in alloy A, whatever isothermal bainitic holding we use, so we always found some martensite transformation, right? So when the microstructure is cooled after bainitic holding. So what you see over here is a dilatation as a function of temperature. So we are cooling from an austenization, like weld is cooled, and we are holding at an isothermal bainitic holding. The bainite is transforming, and upon keeping it for the infinite time, when the bainite transformation saturates, if you cool back, the austenite should not transform to martensite. Unfortunately, for alloy A, you see here 350 and 400. So in both the cases, when we hold it at these temperatures, subsequent cooling led to martensite formation. Right. The other important criteria when we are actually carrying out the electrometry analysis, we also look at the time of transformation. So we cannot keep on holding the weld for infinite time, right? So we'll have to achieve a complete bainite transformation at shorter duration. That means that we'll have to complete the transformation at shorter duration so that no weld can be taken out or the next pass can be deposited. Right, so as you see over here in two cases, we need at least an hour of holding to achieve the complete bainite transformation at 400 degrees or 350 degrees centigrade. Right, so that also gives an indication about the time of holding at these temperatures before which you cannot deposit next weld, or you cannot take the weld out from the furnace upon final welding. So if you look at the alloy B chemistry, we hit a jackpot, right? So if you look at it over here, we can identify MS temperatures again, and we'll have to make sure that the bainitic holding is above MS temperature. We also did that. And if you look at the case 300, where the bainitic holding was at 300 degrees centigrade, so upon holding, so when we cool back to room temperature, there is no martensite formation. So that's very nice, isn't it? Right. So, and if you look at the actual transformation, now we could achieve the complete binary transformation in about an hour. So it's reasonable, right? So what it shows, the dilatation is function of time of holding at these temperatures. So the binary transformation completes. So it's about an hour, right? So this is an ideal condition, isn't it? If you look at the actual the microstructure, so what we are aiming for, the binary microstructure with retained austenite can be ensured in this thermal cycle. Slightly increasing in temperature from 300 to 350, right? We found some martensite peak. That means that the microstructure of this thermal cycle would contain the bainite, retained austenite, as well as martensite, right? So that may not be ideal microstructure because that may induce cold crack when the martensite is present in significant volume fraction. And alloy C, again, it's also nice chemistry. If you look at it over here, so we have MS temperature we predicted, and we kept it in these size thermobaric holding temperatures. And a couple of cases we found very little or no martensite transformation from the dilatation. But for this chemistry, if you look at the actual time of binary transformation is extremely high. For example, in 250 degrees centigrade, we'll have to hold it for close to 8 hours in order to complete the transformation, right? So that is not ideal case, isn't it? So we cannot hold it for 8 hours between passes or after welding because without holding, though, we cannot complete the binary transformation. So with these three exercises, we can already see how we can optimize the weld thermal cycle, isn't it? Right. So apart from the optimizing chemistry, so now with the hot cracking susceptibility studies, we can identify so which chemistry can give us the microstructure without martensite and the bainitic holding temperature and time such that it can be practically used in the welding studies, right? And based on these studies, we can already identify that an alloy B, the weld thermal cycle of 300 degrees centigrade bainitic holding is ideal to get a good carbon-free bainitic containing microstructure, right? So we already optimized this chemistry based on the hot cracking susceptibility studies. Now, based on the electrometry studies, we also optimized the weld thermal cycles, right? So now we can happily weld, right? And so we have chosen now the best weld thermal cycles in all three chemistries, so alloy BT1 and alloy A BT1, alloy B BT1, for example. So the thermal cycle what I show over here. So cooling the welds until 300 degrees centigrade, and then hold it isothermally for about an hour, and subsequently we can cool the weld to room temperature. And by maintaining 300 degrees centigrade melt interpass temperature, so we can also attain the microstructure containing carbon-free bainite and retained austenite. And the microstructure looks very good, very promising, what we obtained. And subsequently, once we identify these isothermal bainitic holding temperatures and time, and we can make the welds and study the mechanical properties again using Gleeble. So we take the weld samples, we use Gleeble compressive tests to identify the mechanical properties. If you look at the three optimized the weld thermal cycles, produce excellent mechanical properties. So the steel B, which doesn't have any martensitic structure at all, okay, showed a very good elongation in compression, right? And with the yield stress is about much higher than what even base material has, okay, about 1,700 megapascal in compression. And so all these three steels exhibited 1.5 gigapascal or above. So we optimize the chemistries, and we avoided hot cracking, and we also optimize the interpass temperatures as well as the isothermal bainitic holding time and temperatures to achieve the mechanical properties in the weld, which is even better than the actual base material, right? So this gives an idea about the use of Gleeble for optimizing welding electrodes, especially in the complex phase containing the ice and steels, right? So we may optimize the chemistries using the simple database-based calculations, but until you see in real experiments, we cannot optimize the chemistries. So from the database, we select the candidate chemistries, and then the further optimization has to be carried out by carrying out physical simulations, say for example in Gleeble. Right, so I showed you a case study where the Gleeble can be very effectively used to identify the chemistries to weld the complex phase containing ice and steel. Right, so the mechanical properties what we achieved using this exercise are much better than the base material in welds. Right, so we made welds, and so the carbide-free bainitic containing the microstructures are welded using these electrodes, what we actually optimized from the study, right? So they even showed much better properties than the welds made using austenitic filler. So with this, I conclude the talk, and I also acknowledge my PhD student who actually carried out this work, and my colleagues, Professor Janakram in IIT Madras and IIT Hyderabad, and my former colleagues, Professor Hemans and Professor Richardson in TU Delft, Netherlands, and of course the everlasting support from DSI and DTS India, so for taking care of the Gleeble, so that now we can carry out such exercises and research activities to benefit the Indian industries as well as in academia. Thank you all for your kind attention, and I hope I gave you a small glimpse of use of Gleeble for welding electrode development. And if you have any questions, please drop your questions in the comment section. I'll be I may present in live to answer these questions. Thank you again. Thank you, DSI, and thank you, DTS, for giving this opportunity.
Thank you very much, Murugaiyan. That's a great presentation. We do have a handful of questions. Dr. Muru, if you can unmute yourself, we can.
Yeah, Dan. Yeah, thank you.
Great.
Yeah. So.
All right. Well,
yeah,
welcome.
I'm here to ask questions. Yes.
Yeah, we appreciate you making that presentation and recording it. I see there were a few questions that were coming in, and you were able to answer some of them directly.
Maybe I'll just repeat the question of Brian, because it needs elaborate answering as well, if I can, Dan.
Sure, that'd be great.
Yeah. So Brian's question is very interesting. So what his question is, did you explore alloying interaction between the base material and filler materials? So that's what we call it dilution. So the amount of alloying elements that are actually coming from the base material, which is actually also molten, and mixed with the molten droplets which are coming from the electrode. So we need to take care of the contribution from the base material as well. So we can calculate the dilution, the fraction based on the welding process parameters what we use, and from the geometrical analysis of the weld when you make the weld in actual material. And we can get that the final weld metal composition from the dilution calculations. So therefore, the exercise what we have carried out, it always involves a range of chemistries with the dilution factor in mind. So even if you have a large dilution or dilution is minimal, so we'll be optimizing the electrode chemistries. So we can use, for example, one of them. If a dilution is such that we can choose the electrode composition or electrodes. So that's the reason why we will not optimize only one chemistry. We'll be optimizing 3 or 4 chemistries, which can give us the microstructure what we want. As Brian, I hope that answers your question.
I'm sure that it does. He had the follow-up question here about what temperatures were the compression tests conducted at.
Oh, those are room temperature tests.
Oh, they are? Okay.
Yeah.
Interesting. There is a question here, and I'll read it. It says, first of all, thank you very much for such a nice presentation, and I agree with that. I am worried about the role of chromium and nickel in the alloys. Can you shed some light on the role of these alloying elements in designing the microstructure of the weldment?
Yeah, so I need to go back to the slide. If you look at the graph, I skipped, the T0 temperature, the allotropic phase boundary I showed you. So these elements can favorably modify the allotropic phase boundaries, and so allotropic phase boundary dictates the carbon concentration of retained austenite during isothermal bainitic holding. So we need to enrich the austenite in carbon as much as possible, as quick as possible, so that the austenite can be stabilized and the transformation can be faster. So the bainitic transformation can be made into faster, so that we can minimize the time at which we hold this the welds at isothermal bainitic holding. So one of the criteria we follow is we need to have the T0 the curve shifted towards large carbon concentration, and to have the retained austenite enriched in carbon. Yeah, so that's one role.
Okay. Yeah. So you had mentioned your presentation. We'll make the presentation available as a PDF. People can download that. What page were you referring to when you answered that question?
So I'm referring to page 8.
Okay, great.
Yeah.
Okay, and that will be available, sent out everybody as a link, as a follow-up email.
Yeah. So the graph we showed you, the role of alloying elements, the effect of alloying elements on the allotropic phase boundary.
Great.
So you can see how we actually played around with the chemistries of nickel and chromium very clearly to have the curves shifting towards the higher carbon concentration.
Okay.
Yeah. So by the way, the work is actually published. So you can also download the paper, and if you are subscribed to Welding in the World. So in the issues, I think a couple of months before it has actually got published in Welding in the World.
Okay, thank you. Question here, it says, I didn't understand how the weld thermal cycle is correlating with heat treatment cycle.
Okay, so so we'll have to go back again, the presentation. When we are doing a multi-pass weld, right? So the first weld, we are not going, I mean, suppose you're depositing in, say, 5 passes, right? So when we are actually depositing a first pass, and we are not letting the first pass to cool to room temperature, right? So we'll have to hold that first pass also, right, in the bainitic holding temperature, so that the first pass would also transform into a bainitic microstructure, right? Suppose if you identify 400 is the IBT, the ionotic isothermal bainitic holding temperature, we would never let any of the welds to cool below 400 in any of the multi-pass welds. The first pass is deposited, and we maintain the first pass also at 400 degrees centigrade, and the second pass is deposited. Okay, so yeah, thanks, Dan, for pulling this slide. Maybe you can move on to the slide number. Maybe 15.
Okay, here we go.
Yeah, so you see over here, say there's a multi-pass deposition of what we made, right? So when we are actually defining interpass temperatures, so we'll have to ensure that the first weld pass is not cooled to room temperature. If you directly cool to room temperature without isothermal bainitic holding, so then it may transform to martensite, all martensite microstructure, right? So then it may crack. So we should not let the weld to any of the part of the weld to cool to room temperature. So the identification of the holding temperature is very critical, right? So we hold it to isothermal bainitic holding, and then we deposit next pass. And after the deposit next pass, again, the weld is not cooled to room temperature. We'll maintain at that temperature. So when all the passes are completed, so we can shift the entire the weld into a furnace immediately at the same temperature. So the interpass temperatures and the post-weld heat treatment holding temperatures are all the same, right? So if you identify 400 is the isothermal bainitic holding, so we'll have to maintain 400, and the weld should never cool to room temperature straight from the, say, for example, solidification, right? We always maintain at 400 degrees centigrade. So that's what we meant about the both interpass temperatures and the isothermal bainitic welding temperatures.
Thank you. We have a couple more questions, and unless some more come in here, maybe these will be our final questions. But it says the weld material is very interesting. How can we make such steel as a base material by conventional thermomechanical processing, followed by cold rolling and annealing?
Okay, so these are the very special materials, right? So there are possibilities of holding at the isothermal bainitic holding, but in industrial practice, it cannot be in a constant temperature, right? So we may cool to bainitic holding temperature slowly, and we extend the time. And sometimes the plates which are actually made can also be transferred and subject to a specialized heat treatment, right? So what I described in one of the slides. So the entire plates, suppose if you're building an armor, okay, so we heated the entire plates in a heat treatment furnace and subject them to the thermal cycles, what I showed you in the first slide, to generate the base metal microstructure. So we may not produce continuous coils. It's very difficult to get this microstructure because sometimes we need hours of holding. So say I showed you a couple of the simulation showed that even say LIC, what I showed you, it requires at least 6 hours of holding. So that's not possible in a conventional say cold rolled the continuous annealing furnace.
Okay, very good. We have a question here from our friends at PSG. It says, for electrode development for a new material, in order to test the material in a Gleeble, how do we find the peak temperature of the material?
So the peak temperature, Dan, I mean, it's not clear. The peak temperature mean the peak temperature of HAZ, or they are referring to the peak temperature which can be reached in Gleeble?
I believe it's the peak temperature of the material. So is it perhaps a melting or casting study? Maybe perhaps nil strength. I'm not sure exactly. So the peak temperature, it's definitely asking about the peak temperature of the material. And I know that the Gleeble can pour enough energy into the specimen so it can obviously melt until the specimen.
Yeah, maybe Dan can pitch in here the peak temperature. So the peak temperature probably, if we refer to NFT temperature, Neil's 10 temperature, so that there are procedures, standard ways, we follow to get the NFT and NDT and DRT. So if it is peak temperature, obviously, the thermocouples, right? So they limit the peak temperatures, and depending on thermocouples, we can identify the peak temperatures that can be reached in Gleeble. Or Dan, if you want to add, you can add as well.
Okay, yeah, and those are, I know, popular tests in the Gleeble, and then for very high temperature materials, we can switch over to a pyrometer as well, which I know a lot our team does that often. So good question.
Yeah.
Another question here for the steel chemistry, the preheating temperature is a must. So the interpass temperature should equal or not lower than preheating temperature. And I'm not sure that's the question, but maybe you can comment on that.
Yeah, so the preheating temperature is also the same as the interpass temperature.
Okay.
Yeah.
Okay, makes sense. And I believe if anybody else has any questions, might be some people typing away right now. So hit enter on that. Otherwise, we will, looks like we're done.
There are a few questions. Yeah, I think there are some questions over here. Okay, so you already read that. Sorry.
Yeah, we addressed those, and we answered some directly. So, but Dr. Moore, again, I want to thank you for the presentation. It was great, and it was great having you here, answering some questions here from our audience. So, thank you. If anyone is out there does have questions about operating the Gleeble, please contact our service team. And I feel obliged. I need to mention this every time. We do have that new service ticketing platform it's available on our website. We have a service portal, and there's a knowledge base in there, as well as a service ticketing system. So if you need service, go to our website and you can sign up for the service portal. If you have any questions about how a Gleeble can support your research, please contact me or one of our metallurgists. We're happy to help you. My email address is dan.quigley@gleeble.com. It's also in the email that went out for the webinar. But again, I want to thank everyone for joining us, spending the time with us here this morning or this evening. And I do hope that everyone stays safe and healthy. Dr. Muru, thank you as well.
Yeah, thank you, Dan, and thank you all for giving this opportunity. Yeah, thanks. We'll certainly keep in touch.
Yes. Have a great day.
Yeah, and you. Bye-bye.